Hey everyone! In this video, we're going to take a look at an alternative method for finding the limit at infinity. Let's just start off with a reminder of what we already know about limits at infinity. We know that the limit as x approaches infinity of the function 1 over x, we know that this is equal to 0. And we also know that the limit as x approaches negative infinity of 1 over x, this is also equal to 0. So in other words, the logic here is as x gets very, very large, since we're doing the reciprocal, 1 over a very, very large number is basically 0. We can get as close to 0 as we would like, as long as we can pick out an x value that's sufficiently large enough. Now, sometimes I cannot always get 1 over x or some form of that in my function. So that's why I want to take a look at some other methods to find limits at infinity. The first such method is using only the variable terms. So I have an example here. The limit as x approaches negative infinity of the square root of 4x squared plus 10, and that's all divided by x minus 5. Okay, so our x values are getting very, very negative. Now, what I mean by only using the variable terms is these two constants, the plus 10 and the minus 5, as my x values get very, very negative, say negative 100,000 or negative 1 million, this plus 10 and this minus 5, they're not going to make that big of a difference. They're not going to change the value of that number very much, relatively speaking. So because we want to know what's happening at negative infinity, I can basically say these aren't going to change my numbers enough to matter. So this is going to be the same as if I look at the limit as x approaches negative infinity of just the square root of 4x squared over x. So now I can basically ignore those constant terms. So our limit written like this will be equivalent to what we started with. And now we can actually do a little bit of simplifying. So in the numerator, I can simplify that square root. So the square root of 4 is 2. So let's see, we're going to get the limit as x approaches negative infinity. So we'll end up with 2. Now, really important here, the square root of x squared, I'll just make a little note. So the square root of x squared, this is not just x. Because we are simplifying within our function, we need to make sure that we treat this correctly, and we actually want to look at this as the absolute value of x. So we end up with 2 times the absolute value of x, and this is all over x. Okay, now let's think about what this function looks like, or what's happening as we plug in different values. So we're at the simplified function. So 2 times the absolute value of x divided by x. And as we're approaching negative infinity, so let's say if I plug in negative 1, okay, this will turn into positive 1 over negative 1, so we get negative 2. Let's say I plug in negative 10. This will turn into positive 10. I'll have negative 10 in the denominator. So I'll have 20 divided by negative 10. I'll have negative 2. If I do negative 100, same idea. We end up with positive 100 in the numerator, negative 100 in the denominator. So hopefully you can see here, for every single negative number I plug in, I'm going to end up with negative 1. And then multiplying that by 2, we get negative 2. So that means our limit, as we approach negative infinity, this is equal to negative 2. Okay, so anyway, this is another method that we can use to find limits at infinity. Because these constant terms aren't going to make that big of a difference when we're looking at really, really big numbers or really, really small numbers, we can basically ignore them and just focus on the variable terms.